celebration day of the 50th anniversary of the Hungarian restaurant. As we all know, it was 50 years ago that Professor Kuhn published his brilliant paper with the title of the Hungarian method for the assignment problem of the Naval Research Logistic Quarterly. Since then, the Hungarian method has become the prototype of a great number of algorithms in combinatorial optimization. Needless perhaps to emphasize how much we are pleased to have Professor Kuhn here, and with how great interest we are looking forward to his lecture on his favorite child. Please, Professor Kuhn, take it.
One of these to use. Maybe this one. If I thank everyone to whom I owe gratitude this morning, my whole half hour will be exhausted. I surely have to thank Andras Frank and Yasmin Zabo, who organized the meeting. And I also have to thank the speakers who were listed a moment ago, who have come from all over the world today. It's really a stellar group of experts in combinatorial optimization. And I really have to thank you for coming out on a holiday. I think I feel gratitude for you to come this day when you could be doing nicer things than listening to lectures on the Hungarian method. Let me get my slides out. I gave the title Reflections on a Favorite Child. Everyone has preferences among the papers they've written, and I like 2 or 3 of mine best, and this is one of the most favorite papers. I think it ranks along with my paper on extensive games and a very odd, obscure paper on sufficient conditions for a convex set, but this surely is one of my favorite children. When I sat down to think of what I would say today, I decided I would reconsider the geometry of the dual to the linear program, which is the assignment problem. And I had 2 objectives in mind. One, I felt I ought to be able to rediscover for myself the Egger-Vary step. And secondly, I wanted to give a new proof of a very beautiful result from Professor H.J. Schmidt, German professor, who may be in the room. Very good. I heard that you were going to be here, and you were going to be embarrassed by the fact your name is going to be mentioned several times. Very beautiful proof that an Edgar-Vary step is a steepest descent direction. So those were the objectives I set myself a few weeks ago, to reconsider this problem in this light. We have to make sure we're talking the same language here, so I have to present a slide with some notation and definitions so that we know what we're talking about, because I'd like to talk a little precise mathematics. Can you hear me without the microphone? I'd rather stand back so you can see it. Can you hear the background? By the way, I know from my own linguistic problems here, I don't understand Hungarian, and I suspect there are a fair number of people in the room who do not understand spoken English. I'll try to speak slowly and clearly, but almost everything essential will be on the slides. So you have the opportunity either to try to concentrate on what I'm saying, or you can try to read the slides. Probably not both. Anyway, the data of the assignment problem is a real n by n matrix with entries rij. And we want to maximize the sum on ij of rij, xij, subject to the condition that the row sums of the x are 1, the column sums of the x are 1, and the xij are non-negative. Well, we all know that this convex set, the feasible set of this problem, is the convex hull of the permutation matrices. And in a linear program, you'll get some optimal solution at a vertex. And so you will find an assignment which maximizes the total rating sum, the sum rij, xij. The dual linear program has variables for the rows and columns, ui and vj. And we want to minimize the sum of ui plus vj subject to ui plus vj greater than or equal to rij. Now these dual variables are unrestricted. They're not necessarily non-negative. You can make them non-negative in a variety of tricks, but as it stands, this dual problem has a difficult geometry. If you have a feasible solution with ui plus vj greater than or equal to rij, you can increase all the vj by a certain amount and decrease the ui by the same amount and still get a feasible solution. This means that the feasible set for this dual problem contains lines that go off to infinity. And there's a lovely theorem which says if a closed convex set contains a line, it does not have an extreme point. And this is necessary and sufficient. Either it contains a line or it has an extreme point. So this dual program has no extreme points. And we're not in the realm of the simplex method or any such algorithm which goes from extreme point to extreme point. So, as I've said, the dual contains a line and hence no extreme points. And the last thing I wanted to show you is the notation, a very useful matrix W. Wij is the difference between ui plus vj minus rij. And this appears prominently in the story. It's a very useful matrix. So that's the setting. And because a great deal of what I'm going to say deals with the Eggervari step, I want to show you on the next slide some precise definitions of what I mean by an Eggervari step. Otherwise, the statement will have no meaning. Even Professor Schmidt's theorem has no meaning unless you know what an Eggervari step is. So bear with me. I know there are a number of people even more expert than me in this room and have been working for longer than I ever did on the assignment problem. Bear with me if I repeat some very fundamental facts. And it will also give an abbreviated account of how I discovered the Hungarian method. Reading Herring's book on graph theory, I realized that his theorem about matching of bipartite graphs was a special case of the assignment problem. That is, if you have a rating matrix which has only zeros and ones in it, which might have a very easy interpretation that 1 means the individual is qualified and 0 means the individual is not qualified. Then the maximum number of ones you can choose, no two in the same line, is equal to the minimum number of lines, rows or columns, with which you can cover the matrix. And that's Koenig's theorem, and I realized he not only recognized this duality, but he gave an efficient algorithm for finding minimal covers and maximum matchings. I thought, gee, if I can only find a way to reduce the general problem to this special case, I'll have a good algorithm. Now there's a point that I think must be made here that's not on any of the slides. When I was working on the problem really in 1953, I think many of us had motivated motivation to construct efficient algorithms. I don't think that was ever a motivating factor for Koenig, and surely not for Egervari. They were doing pure mathematics of duality, really long before linear programming was invented. But they had no push to develop a good computational method. There were no computers around. In '53, there were already very primitive but fast computers. When I was reading Koenig, I was at the Institute for Numerical Analysis at UCLA, which had a computer that had 256 words, 8-bit words of memory. The entire memory consisted of cathode ray tubes with 256 words of memory. And somebody at the Institute was trying to enumerate all permutations on 10 elements, and he couldn't program the computer to do it. I mean, it's very hard to go back to those days, but nevertheless, we knew they were going to get better. And so it was important to construct algorithms to solve problems. Anyway, that was motivation. Well, in Koenig, there is a footnote saying that Egervari has generalized this result. And I took it out of the library and read the German summary, and it didn't tell me everything I wanted to know. No, I was very impatient. I wanted to find out what was in this paper, so I got a large Hungarian dictionary and a large Hungarian grammar, and I translated the paper. And lo and behold, in the middle of the paper is an argument that runs like this. I'll uncover the rest of the slide in a moment. He said, construct a dual feasible, UI and Vj. Look at the matrix W. If there are n independent zeros, no two in the same line in that matrix, then that is an optimal assignment between it, because the two objective functions are equated. Otherwise, you can cover with fewer than n lines, n minus 1, he said. And he gives a constructive step to improve the UI plus Vj based on that cover by n minus 1 lines. Eureka! And that was a moment in which I knew I had a good algorithm. I didn't have to do it for n minus 1. I could do it for any cover which was less than n lines. And this is the Egervari step. As I was telling someone this morning, I went up to my study and I started solving 12 by 12 problems, generating 3-digit numbers and solving them in about an hour and a quarter of hand computation. When I did that, there was no computer in the world that could solve a 10 by 12 by 12 assignment. I knew I had a good algorithm. But let's see what the precise definition of the Egervari step is. Given feasible dual variables, construct a maximum set of zeros in W. W, you remember, is UI plus Vj minus Rij, with no two in the same line. And at the same time, by Koenig, construct a minimal, this is done by alternating paths, surely everybody knows that. And a minimal cover of R rows and S columns. May I interject a deficiency in the Hungarian language? One of the few words I remember from my translation of the words for row and column. And they ought to start with R for row and S for column, but it's just sor and rom, wrong. Otherwise it'd be nice. R rows and S columns. If R plus S is n, if you can't cover with fewer than n lines, then the maximum set of zeros is optimal. You have a complete assignment. You assign on where the zeros are. Otherwise, you perform an Egervari step. And the way I will define an Egervari step is you increase the dual variables in the rows which are in the cover, and you will decrease the V's in the columns which are not. And if you do that, you decrease the objective function by the difference of n and R plus S times epsilon. And you can go as far these, of course, elements contain those zeros because there are rows in S columns contain all of the zero. They're all positive. You can go as far as the minimum of the positive entries in that area. And that, for me, is a negative R step. Of course, you can reverse the rows of rows and columns and increase the V's for J in the cover and decrease the U's for UI not in the cover, but that's actually is equivalent to changing the V's and U's in the way I said moving along the line. That doesn't give you any greater generality. So if we're going to understand what I'm going to say from now on, those are the rules of the game. This is the definition for me of an Egervari step, and the Hungarian method is the combination of Koenig steps and Egervari steps to go to an optimum for the assignment problem and for the dual problem. Now I can talk about Professor Schmidt's result. His thesis in 1974 and his paper in discrete mathematics in 1978 defines, as I did, a minimal cover. But he also says each Egervari step using any minimal cover chooses a norm direction of steepest descent. I think this is the main result of the paper. He does it for the transportation problem, but clearly the assignment problem is a special case. But that is the main result of the paper, in my eyes. There are other beautiful things in the paper, lovely geometry, but that's the main result. I'd like to show you now an example I constructed, thinking I could provide a counterexample to his theory. So I'm going to put up an example. Now, this is a 5 by 5 example, and this is the matrix Rij. The first thing we have to do is construct a feasible dual solution. And that's easily done by choosing the row maximum in each row. It's 4, 4, 4, 4, and 4. And lo and behold, we don't have to subtract anything from the columns because we've already achieved the maximum in each column by these 4, so the Vj are 0, 0, 0, and 0. And then I construct the Wij for this matrix. And here it is. You ought to be able to see very easily. At least there are actually 4 minimal covers of this. But you can see one immediately right here. If I use these 2 rows and these 2 columns, then that's a minimal cover. You cannot construct more independent zeros. There are only 4. That covers all of the zeros, so it's minimal. And so an Egervari step for this cover, we'll use an epsilon which is equal to the minimum of the entries which are not covered here, and that's 1. So I will add 1 in these rows and subtract 1 in both of the columns. But this example is constructed so there's a better Egervari step. If I use this cover, covering by the and the first row, covering by the first row and the first, second, and fifth columns, making a change of epsilon in the first row and in these 2 columns, 3 and 4, I can go as far as the minimum of this uncovered area. I can move 2 units. Indeed, I go to an optimum. That is, if I choose +2 here, and -2 here, and -2 here, I go directly to an optimum. Everyone would agree that's a better Egger-Varry step than the first one. And elementary conclusion, which is not very precise, is that not all Egger-Varry steps are equivalent, or not all Egger-Varry steps are equivalently good. Let me be a little more precise of what I was thinking at that time. It's very naive. The rate of change, or the rate of descent, is the change in objective function divided by the length of the move. And I confess that I was thinking of lengths in Euclidean distances. So the first Egger-Varry step improved the objective function by 1 with a move of the square root of 5, because there were 5 components, 2 rows and 3 columns changed. The second Egger-Varry step changed the objective function by 2 in a move of 2 over the square root of 3, and it's clearly better as a rate of descent. Why is it not a counterexample to Professor Schmidt's result? Well, I have to put up a slide that almost embarrasses me in a sophisticated audience such as I'm confronted with. But it has to be said in this way to be precise what we're talking about. What are we talking about in steepest descent? We're talking about a change in objective divided by the length of the step. But we have to answer the question, step is in which space and how is length defined? Now, I had read Professor Schmidt's paper more carefully. When I constructed this example, I would have realized a Schmidt step is in W space, which he makes into a norm linear space by using the norm of W as the maximum absolute value of any entry in the matrix. Now there are other choices. I used a different space and a different measure of length, a different norm. That is surely one possibility, to use the space, the UV space, and the Euclidean norm. There's this third kind of mixed possibility in which we take a step in the UV space, but we use the maximum absolute value norm. Maximum of the absolute value UI, absolute value EJ. So that there's 3 alternatives, and we get very different results depending on which choice we make. We've seen Schmidt's statement, which is true. We've seen an example in which Egger-Varry steps are distinguished by being better or worse in this choice of space and norm. I decided to find what's the best you can do with this choice of space and norm, and I calculated it was, I won't go through any of the details of this calculation, but you'll have to trust me. There are 2 extreme two extreme steps, which are not Egger-Barry steps. This one adds 1, 0, minus 1, minus 1, 1 to the u's, and 1, minus 1, minus 1, minus 1, 0 to the v's, and takes you straight to an optimal answer. There is another optimal. These are the two extreme steep descent directions for that problem. With the steepest descent using the UV as the space and the maximum absolute value as norm. This one is also not an Egger-Barry step. But both of them carry you directly to the optimum answer in one step, using only entries which are 1 and minus 1. And so they have a descent rate of 2. Remember that the maximum descent rate of an Egger-Barry step in the W space with the absolute value norm is 1. So these are somehow both better. I have a favorite. I went to the midpoint of these two. They're two extreme. I went to the midpoint. And this is my favorite. Adds 1 to U1 and subtracts 1 from U3 and U4, and adds 1 to V1 and subtracts 1 from V3 and V4. This is performing two Egger-Barry steps at once. That is, I gave you a step in which you increased by 1 and decreased by minus 1 here. There's another symmetric one in which you increase the V1 by 1 and decrease U2 and U3 by 1. You're performing two Egger-Barry steps in one using this change of the dual variables. And of course it carries you to an optimal answer. With a Euclidean norm, it gives a change of 2 for a Euclidean move of the square root of 6. It's even better than the one I showed you before, because the Egger-Barry step I gave you before gave a change of 2 for a Euclidean move of 2 times the square root of 3. I'm watching the time very carefully. So it's time to make a conclusion. Okay, no, I want to play by the rules. Okay. I timed this carefully for that. Trying to give you the essence of what I want to say. The essence of what I want to say is that these choices of space and norm give different results. And it is not quite clear that the Egger-Barry steps are very simple and they're immediate to calculate. They have an enormous simplicity and beauty in that regard, but they are not necessarily the best steps that can be computed. And it differs by the nature of the choice of the space and the norm you use. About 30 years ago, with Richard Kuhn, we did a set of experiments on the simplex method. I have a slide giving the reference to these papers. I boxed the one which is, I think, most important and has the most detail. In essence, when you choose a pivot in the simplex method, you look for an entry in the tableau which is positive, and you pivot in that column in a manner which maintains feasibility. But you can choose the best rate of increase, which requires a little bit of more calculation. Or you can try to maximize the gradient of your change. And we solved something like 10,000 linear programs using these different pivot rules, using different gradient methods, the gradient in the space of basic variables, the gradient in the space of all variables, And we found that the gradient methods didn't matter very much which variables you chose, beat all the others. We were using a Euclidean distance, but it beat all the others both in time and in pivoting. It beat the best increase, which requires more computation. It beat the usual simple rule, but by a whole lot. And this was all statistically significant. And I guess what I'm proposing here that is we might broaden our view of the Hungarian method to look at other choices of modified Egavari step that you might find better performed. In a example 5 by 5, I'm stuck with that throughout the lecture. Not going to make much difference what the hell you do. You get there in 2 steps, even if you're dumb. But if you have a problem that's 100 by 100, it may well make a difference how many steps you perform. Anyway, that is my conclusion. I thank you all again for coming out.
Other question or remark?
I think Professor Schmidt should have an opportunity to defend himself. I was very happy I did not find a counterexample.